improved image. All right, some message coming. This meeting is a recording. I agree with the recording.
Thank you, sir. Thank you, sir.
Okay.
Sorry for the interruption.
So yeah. Okay. Okay. So also we use a digital holography technique to measure some physical quantities. This in this graph shows the thickness and refractive index are measured simultaneously. This one shows the shape of the small object. This is for the measuring the polarization. This picture shows the Mueller matrix. And also we try to the digital holography to record the color three-dimensional object. And also we are researching on holographic data storage to record a lot of data, so SNR and light utilization efficiency is improved. And also multi-recording using CGH techniques like this. So we have a lot of papers. So if you are interested in our topics, please check my name on the Google, Takanori Nomura, Wakayama University. And also we studied on non-interferometric wavefront phase sensing, Shack-Hartman, and today's talk, TIE, transport intensity equation. And also today talk about the computational ghost imaging, CGI. So here is outline my talk, real outline of my talk. First, I will show you the real introduction of my talk. Then I will give you a brief review of the phase imaging based on transport intensity equation, TIE. I will mention that some problems of TIE for phase imaging is remain. This is the motivation of my talk. So I will show you 4 kinds of our TIE techniques. The use of multiple bandpass filters, the use of optical parallels, the use of polarization directed flat lenses, and transport intensity computational ghost imaging. To help understand computational ghost imaging, one of our achievement of computational ghost imaging will be given. Finally, I will summarize my talk. So, as you know, phase imaging is a significant information to analyze structure of the transparent object. Although phase contrast microscopy enabled us to observe phase objects, the information is not, unfortunately, quantitative. So interferometry is used to achieve the quantitative phase imaging. However, it is often bulky because of its complicated optical experimental setup, including reference arm and object arm, and suffering from an wrapping problem of the phase. On the contrary, the transport of intensity equation, TIE, describes the relationship between the phase and the first derivative of intensity with respect to the optical axis under the paraxial approximation. This technique achieves a phase retrieval directly from intensity images obtained at in focus and several defocus positions. And it also can avoid wrapping problem. So let me move to phase imaging based on transport intensity equation. This is, we have a phase object like this. This is a phase 0 to 0.5 pi radian. So if we focus of this object, we cannot see any information, uniform intensity like this. However, we move the imaging camera, so we defocus of this object. You can see, oops, sorry, oops. You can see something go here. It is a defocus images. So we can see, obtain something from information. It is a phase information if the object is out of focus. In focus, we cannot see anything. Out of focus, moving the camera, we can see something from phase information. This is a basic idea, basic concept of transport of intensity. TIE gives a relationship between the phase information and out of focus images mathematically. So I will show you some equations to the relationship between the phase information and out of focus images. A little bit complicated. You don't have to understand completely. Anyway, I will show you some equation. This is the transport of intensity equation. The TIE derives from paraxial Helmholtz equation and described by this form. Here, Iz is intensity in plane. Phi z is desired phase distribution to be measured. In this case, the object is placed at z equals 0. Lambda is a wavelength. Nebula denotes a two-dimensional gradient operator by definition. T can be solved the phase phi 0 using Fourier technique. So we obtain this equation. This is a equation which gives the phase phi 0 using Iz I0. Intensity derivative Iz Id is approximately calculated from this equation because the derivative cannot detect directly. So we substitute the finite difference, and also another technique can be available. So anyway, this equation is very important to measure the phase from the intensity and the intensity derivative. But this is a finite difference method using two intensity informations, I0 and I delta Z. So we have to move the image sensor along the optical axis. This is some problem because the movement should be very precisely. We move over the pixel size of the image sensor, it causes big errors. So it is very precisely move this image sensor along the optical axis. It is a problem. So this view graph shows the important things of TIE. I show you this equation again. So we have to detect I0 and DIZ, DZ. I mention again to obtain in focus and out focus images. We call this images through focus images. So straightforward method to obtain through focus images is scanning along the optical axis of image sensor or an object. Object moving is not practical, so in general, we have to move the image sensor on the optical axis. So it requires accuracy within the pixel size of an image sensor. So this is not good for recording of dynamic phenomena. So this view graph gives more details to obtain approximate DIZ, DZ. The common method is a finite difference method. So second order, fourth order, any order you can use. But in general, two order, second order, and maybe second order is common. But you can use any orders. So you detect out of focus images more than two, you can use fourth order central difference finite difference method. But in this case, the delta Z is equal intervals. But sometimes, due to the experimental conditions, the delta D is different from each other. So in that case, we can use polynomial approximation method for DIZ, DZ. So in this case, 1, 2, 3, 4, 5 data we obtain. So nth order polynomial approximation by least square method for all pixels. So for example, 1, 2, 3, 4, 5 data, third order polynomial approximation can be applied. So then the derivatives can be calculated for all pixels like this. So the preparation is okay. IZ and out of focus images can be obtained. So we can calculate the phase information. So from now, I will show you some techniques of our achievement. Today, I will introduce 4 kinds of approaches to mechanical scanless TIE phase imaging. We don't have to move the image sensor. So first one is the use of multiple bandpass filters. So this is a paper. The details can be checked in this paper. So 1, 2, 3, 4, and before the last one, I will give you the computational ghost imaging with low spatial frequency mask. This is amplitude imaging, but it is useful to understanding the last topics. All right, let me move to the first one, multiple bandpass filters TIE. So in general, chromatic aberration is troublesome for imaging. However, in this research, chromatic aberration is positively utilized. Please pay attention to the picture. The object is imaged in focus for green light, lambda 0. But another wavelength, blue one and red one, out of focus because the lens has chromatic aberration. Green for in focus, blue and red for out of focus. So we can apply TIE these images. This is an idea. It's a very simple idea for multi-band pass filters TIE. This view graph shows the experimental setup. This one. We use multiple bandpass filters to realize different wavelengths illuminations. So this is a white light source coming from here to show the spatial light modulator phase type. So we display phase object on the SLM. So then the light coming from the left side to the right side. So we use bandpass filters. So in this case, 1, 2, 3, 4, 5 bandpass filters. The central wavelengths 520, 568, 620, 671, 730. The full width of half maximum is 10 nanometer. It's very short, very small bandpass, very sharp, almost monochromatic. So another specification of the experimental setup, it's a very common, not so special devices. Pixel size of image sensor 4.5 micrometers. The number of pixels of image sensor 1280 by 960. The pixel size of SLM 20 micrometers. Number of pixels of SLM 800 by 600, and so on. The lens is made by BK7. It has chromatic dispersion like this. So 520, 568, 620, 671, 730, different refractive index. So it has chromatic aberration. So we use some, this is an in-focus image. Number 1, number 2, defocus image. We can obtain DIZ, DZ using finite approximation using this equation. Sometimes we can use 5 data for finite approximation. Anyway, I will show you the experimental details. So we can use more than three for approximation. Number 1, 2, 3, 4, 5. And also we try to use polynomial fitting, first order and third order using 5 measured data. Here, experimental result. This is a phase object. Number 1 phase, A, phase A, phase B. Phase A is a very gradual phase distribution, like a Gaussian. This one is a little bit sharp. It has a high spatial frequency component in this phase object. Here is through focus images for object A and object B. It is very difficult to see the difference, but the focus position is different. For object B, you can see some differences. This is information. This is the defocus information. For the defocus images, you can see the letters TIE, TIE. So this is something from phase information. So we calculate, reconstruct phase information from these images. So you can see some data. This is a finite approximation method. So 1, 2, 3. This is another finite approximation method. 1, 2, 3. The bottom one is using a polynomial approximation, first order fitting, third order fitting. And this is safe for different object B. So in this case, the first order fitting is a very good result. So less error from the object. But any types, you can see the phase information from the data. But pay attention the right. This is not good because the phase value is different for two phase objects. This is the same phase values. So in this case, is good result. So this is the TIE multiple bandpass filters. The TIE-based phase imaging using multiple bandpass filters was proposed. The proposed multi-band TIE achieves the quantitative phase imaging by only changing bandpass filters. We can, we don't have to move the camera. So the idea confirmed by the optical experiment, low and high frequency phase objects were retrieved by the finite difference method with 3 images and polynomial fitting with 5 images. So the result of the experiment shows the polynomial fitting with approximate degree of polynomial gives better accuracy. For stable imaging quality, the optimal wavelength, optimal degree of polynomial need more details in investigation. If you are interested in this topic, please refer the paper published in 2016 Applied Optics. Okay. Now let me move to second idea, optical parallel. This technique cannot not published in the journal paper, but we already presented at some conferences, Information Photonics 2019. It was held in Yokohama, Japan, last April. Anyway, this topic is very simple. We can use optical parallel. So the beam is coming here, passing through the object coming here. A portion of the beam reflects the surface of the optical parallel, and the rest beam reflects the bottom of the optical parallel. So we can obtain in focus and defocus images simultaneously without image sensor scanning, like this. The optical path difference defocus distance delta z giving by this equation. T is the physical thickness of the optical parallel, N denotes the refractive index of optical parallel, theta is the incident angle, theta 1 denotes the refractive angle. The distance between two images. If the distance is too small, the two images overlapped is not good. If the X is too large, we cannot record the two images simultaneously. So the distance is given by this equation. So we can adjust the X and delta Z by refractive index N and physical thickness T, but it is not practical because the optical parallel is fixed. So the thickness change is not easy, and also refractive index N change is not easy. So which is important, delta Z or X? Actually X, I mentioned before, too small, too short is overlapped. Too large is cannot obtain whole images. So incident angle theta is adjusted to the condition to satisfy the condition of these images. Oops. This is not good. This is not good. So incident angle is properly selected. We can obtain these images. In focus images, out of focus images simultaneously within the image sensor area. So we extract of the images in focus information out of focus information. So we apply TIE to retrieve the phase like this. So let me move to the experimental setup, experimental result. In this experiment, also a phase type SLM was used for a phase object. Actually, SLM is a refractive SLM. In the previous topics, the optical schematic diagram is correctly shown. But in this case, to simplify, the SLM is treated as a transparent type SLM. Anyway, here we have an optical parallel. In this case, thickness 12.7 millimeters and the refractive index 1.54. The incident angle was set to 13 degrees. In this case, 13 degrees incident angle, thickness 12.7 millimeters, refractive index 1.54. The defocus distance delta Z is 38.7 millimeters. Actually, this distance is too long for TIE, but we cannot adjust delta Z. Here is the experimental result. This is a given phase distribution. This is captured images. In focus images, defocus images. In focus image, defocus images. So we apply TIE, we obtain retrieval phase distribution. So this is a similar phase distribution was retrieved. So I will summarize TIE phase imaging using optical parallel. We have shown scanless TIE based on phase imaging using an optical parallel. The experimental was carried out. The intensity distributions were captured simultaneously. The phase retrieval was achieved. So this is the second topic. Okay, this is the third one. Previous one, we use optical parallel. In this case, we use polarization directed flat lenses. Polarization directed flat lens, PDF. PDF has a positive or negative focal length based on the input polarization. If the right-hand circular polarization is coming, it works as a positive lens. Left-hand circular polarization is coming, it works as a negative lens. One lens has two focal lengths, so we use this lens for TIE. PDF lens is not so special. You can purchase from Edmond Optics. It is commercially available. This view graph shows the optical setup. We have a PDF lens here. This is the same optical setup. If we use a left-hand circular polarization, the PDF lens has a negative focal length, so the optical beam is like this. Right-hand circular polarization optical beam is through this line. So in this case, in focus, in this case, the defocus. We change the polarization state. We use quarter wave plate rotating. So the image sensor is scanless, but quarter wave plate have to move 90 degrees. So this is a very simple optical setup. Just insert the PDF lens in this position. So this is a optical experimental result. This is an object to be measured. This is a real phase object. This is a microdot lens. Dot and gaps have different optical path lengths. This is one design that different optical path lengths, namely different phase. So in this case, we use left-hand circular polarization. The right one is using a right-hand circular polarization. Due to some constraint of optical system, we cannot obtain in-focus image. Both are defocus image, but we can obtain retrieve phase information to different out of focus images. We measure phase distribution of the object using TIE, these information like this. This is a proposed method, namely using PDF lens. This is a conventional method. Conventional method means the interferometric. No, I'm sorry. This is a conventional scanning image sensor method like this. The blue one is the proposed method. The orange one, triangle one is a conventional method. The cross section is this one. This is cross section. I hope you agree the profiles are very matched. So this result confirms the usefulness of the use of PDF lens for TIE phase imaging. So we presented the TIE-based phase imaging with PDF lenses. In this proposed method, only switching the polarization states of incident light allows us to obtain two intensity distribution at different depth positions without mechanical scanning of image sensor. The qualities of the phase distributions were compared between the conventional and proposed method by optical experiment. The results show the distribution obtained by the proposed method is quite similar to the conventional method. So the feasibility of the method was confirmed. This English is quite funny. Don't have to this work, but if you are interested in this topic, please refer to the papers published in 2020 in Applied Optics. All right, let me move to next one. So this is a kind of introduction for the last topics, as mentioned before, computational ghost imaging. I will give some brief review. This is the outline of ghost imaging. It is used for imaging under weak illumination. Conventionally, normally, imaging by using an image sensor, it's a camera. So like this. So a lot of pixels is here. So many point detectors are there. Small detected intensity for each pixel. So this camera, normal camera, is not available under weak illumination. On the contrary, ghost imaging does not use camera, area sensor, image sensor. It is point detector, bucket detector, like a photo detector. Single photo detector is used for detect the collected light. So in this case, the intensity is larger than this one. So imaging is available even under weak illumination. So it is useful for biomedical imaging, low invasive imaging, or astronomy area, measuring of faraway celestial object. So this is a ghost imaging keys using only the point detector, bucket detector. This is GI, this is the CGI. Ghost imaging using some diffuser to make a speckle, like a speckle pattern. So conventional GI to detect the speckle pattern by the CCD camera. So then calculate something to retrieve the image. But now we use the two-dimensional SLM to generate some random patterns. So the computer controls the random pattern and the computer knows the random pattern. So we don't have to, this CCD camera used in ghost imaging. So computational ghost imaging is very useful for, and also optical system is very simple. So now almost researchers use this CGI. Ghost imaging is not so common in nowadays. CGI is very popular. So this is a typical CGI optical setup. We have object here. In this case, object is a amplitude object. So its transmittance is T, XY. This is a transmissive SLM put on an object. This makes the random pattern to achieve the computational ghost imaging. The random mask is displayed on this SLM. IR is a random amplitude mask displayed on the SLM. It consists of the transmittance 0 or 1. In general, typically 1 or 0. Sometimes 0 to 1. But to change the mask very fast, binary SLM is preferable. So this pattern has a 0 or 1 transmittance. The light power BR is detected by the bucket detector coming through the right, left side, collected by the lens. The bucket detector can detect the intensity information. And we change the pattern, so detect the change the pattern, detect the intensity. This one, change the pattern, the intensity is also changed. So lots of measurement, after the lots of measurement, we can retrieve the object using these equations. Reconstruct T, object transmittance using relationship IR and VR. The function approaches the object intensity with lots of measurement. You can see some cartoon of ghost like this. So this view graph shows the pros and cons of CGI. Pros, CGI does not require a camera. The techniques makes it possible to simplify an optical setup and also useful for weak illuminations. But it has cons. CGI requires a large number of measurements, typically 100,000 times and more. It's a long computational time for large image. It may be a few hours or more. It is problem. So our motivation to obtain an image with a small number of measurements, we propose CGI with designed low spatial frequency masks. This view graph shows, oh, no, sorry. This view graph shows the proposed idea of our CGI, designed low spatial frequency mask, LSFM. This is a conventional random mask. This is our designed LSFM. So in this case, the change of the intensity is not so significant. But in this case, the change of the intensity is significant. So change the intensity, but change the random mask, but the change of the intensity is very small, not significant. But in this case, the random pattern is drastically changed. So the intensity, the intensity is very different like this. So our approach, the use of a not random, but somewhat designed amplitude, still random mask. So variation of intensity, conventional one small, but in this case, our approach is large. So we expect the number of measurements can be reduced. This is a optical setup to confirm our idea. We have a SLM here. This shows the random mask, proposed one, LS, FM, and the conventional one, quite random. The number of pixels 64 by 64, not so much because we use a lot of numbers. The experimental takes a lot of time so 64 by 64 is a reasonable pixel. And also the object is here, cartoon ghost. Light source is a very normal helium laser. So to achieve weak illumination, we use a couple of ND filters. So in this case, the transmittance is 1/10,000. We didn't use the bucket detector, so we used the CCD camera as a virtual bucket detector. Detector size is 0.33 by 0.33 millimeters, corresponding 70 by 70 pixels of the CCD camera. And the number of measurement is 10,000. This is a experimental result. Proposed one, you can see some ghost cartoon over 5,000. 10,000 enough to see the ghost. But conventional method, it is very difficult to see the cartoon of ghost. Barely you can see the ghost right hand here, but it's not good. So you can see the object by the proposed method. This confirms the feasibility of the proposed method. Then we evaluate quantitatively. This is a conventional one. This is a proposed one. Root mean square errors confirmed the feasibility of the proposed method. So computational ghost imaging with designed amplitude mask was proposed. Owing to the designed amplitude mask, the number of measurements can be reduced. Optical experimental result confirmed the proposed method qualitatively and quantitatively. But in this case, we can retrieve only the amplitude object. So this technique cannot apply to phase image to phase object. So phase imaging is not available in this CZI. So try to achieve phase imaging using CGI is our motivation to the next topic. This is the last one, transport of intensity computational ghost imaging. So as mentioned above, CGI allows to image an object under low signal to noise ratio, such as weak illumination. It is expected that the CGI apply to non-invasive imaging of living cells. However, only amplitude information can be obtained by the CGI. And also, it is difficult to image to transparent objects by the CGI. This is the same meaning. We achieve the imaging by applying the quantitative phase imaging to the CGI. I made mistake. TIE to the CGI. Significant. TIE. No. Quantitative phase imaging using CGI to the TIE to the CGI. Slight modulation of the optical setup. Let me move to our idea. This optical setup is a conventional CGI, SLM, and object. This is contacted with two object and SLM. But our idea is move to the object like this. Object on the SLM is conventional CGI, but our TI CGI object is the front of the SLM. This is key point. The Hadamard mask is displayed on the SLM. Random mask is also okay, but in this paper, we use Hadamard mask like this. It has a 0 or 1 transmittance like this one. The intensity measured by the point detector, same as CGI. And step 1 and 2 are repeated with different masks. Same equation to retrieve the transmittance of the object. But in this case, the information is retrieved. Namely, this function approaches the out of focus intensity with R approaches to M. So, out of focus, this is the object. But the intensity can be retrieved by this optical setup. So this is our idea. Same equation, TIE. But in this case, object is here, SLM here. We can detect this information. So we cannot obtain I0. I0 is a in-focus intensity distribution by this optical setup. Only defocus intensity distribution can be obtained. Therefore, intensity of in-focus distribution is approximately estimated by averaging defocus intensity distribution. Because in-focus intensity distribution is unity, no distribution, only one intensity distribution. So it is reasonable to estimate by averaging the defocused intensity distribution. This is a numerical simulation. This is a phase object like this one. Yeah, dot length simulated. So this is a defocus image by using TICGI, this optical setup assumed. Only this is a numerical simulation. So mean value is a 0.67. This is virtual in focus intensity distribution. So by using these images, we retrieve phase distributions by TIE like this. The cross section of the green line show this area. This is a true phase distribution, and this is a TICGI phase distribution. You can see almost same distribution of the cross section. So the numerical simulation confirmed our idea in focus image distribution and phase distributions. So let me move to optical experiment. Yes, micro dot length to be measured. Same optical setup in the numerical simulation. This is a retrieved defocus intensity distribution by using this equation. In this case, we achieved the weak illumination conditions, 100,000, 1/100,000. So we retrieve phase distribution using this one and the virtual in focus intensity distributions. So the cross section is here, shows here. The orange triangle denotes the TICGI. To compare the phase differences, we measure the phase information by using phase shifting digital holography, this one. The blue circle denotes the result by the phase shifting DH. The resolution is very different. Phase shifting DH has high spatial resolution because it is the same as the pixel size of the image sensor. But CGI is spatial resolution is depend on the SLM. In this case, SLM 64 by 64 pixels, so the resolution is not so high. But I hope you agree the phase difference is similar to each other. So this experimental result confirm our idea. So let me summarize TI-CGI. We have proposed TI-CGI for phase retrieval under low signal to noise ratio condition. Numerical and optical experiments have been performed. In the optical experiment, the retrieved phase distribution was compared with the phase shifting digital holography. The result shows the proposed TI-CGI can be used for retrieval under low resolution. All right, so I told 4 kinds of our TIEs. This table shows a comparison of 4 approaches. The use of multiband pass filters, optical parallel, PDF lens, TICZI. All approaches is without image sensor scanning. Yes, no scanning. What changes? This one is a filters, no change. Optical path difference, path length change, passive optical parallel. In this case, polarization is changed. This is the random mask, Hadamard mask will be changed. Optical setup, this one simple, little bit complicated. Additional optics, bandpass filters, optical parallel, PDF lens, etc. So the merit is denoted by red letters. Demerit is denoted by blue letters. I will not mention which is the best. It depends on the application, up to you. I have shown 4 kinds of image sensor scanless TIE imaging. This is conclusion. The use of multiple bandpass filters and so on. These approaches can be useful for phase imaging of the dynamic phenomena. Actually, this is suitable for dynamic phenomena. This one changes the filters, changes the polarization. Slow dynamic phenomena is good. This takes a long time to measure the one phase distribution. So this is the grown up bioplant, very slowly dynamic phenomena is only can detect. So before closing my talk, I will show you some our recent published papers. They are researched on holographic data storage. This is a CGH. This is the incoherent holography, phase imaging. So if you have interest, please refer these papers. This is an acknowledgement. The achievement accomplished by our colleagues. This is Professor Saita, and this one is another good student of my laboratory. So we have a student chapter like you, MNIT. So that's all. This is my talk. Thank you for your kind attention. Thank you.
Thank you, Professor Takanori. Thank you for your for sharing your knowledge and your research work with us. We are very grateful to you. And now question answer session are also open. We have some few minutes for question session. So if anybody wants to ask some question, they can access the question answer session and ask. Yeah, we have one question. Say, Professor, one of our
Yes.
attendee wants to ask one question. Is quantitative
Okay.
phase retrieval with TIE better than the interferometer? Am I clear?
You mean the accuracy is which is better, interferometer or TIE?
Yeah,
Your question is
yeah, that's what he want to ask.
yeah. Actually, interferometric technique is best because TIE is uh, obtained by some approximation because it's partial approximation is mandatory. So it has some error to obtain the phase distribution. But if you need only the relative phase, uh, for example, uh, large phase, middle phase, and small phase is enough, so you can use a TIE. But you have to know the exact phase difference between two positions. You have to use interferometric technique, including digital photography and uh, something.
Thank you. Thank you, sir. So if anybody also wants to ask, they can also mail their question to us through our email ID osamanitj@gmail.com. So now we have one thank note from OSA student, OSA MNIT student chapter. I would like to thank Professor Takanomori for taking such a great effort uh, for to put this webinar in such a lovely manner and sharing his knowledge and research work with us. We would like to welcome him in person in our university, MNIT Jaipur,
Yeah.
as soon as this pandemic
Yes.
get over. So thank you so much, Professor. And now we are
Thank you.
ending our webinar. And there is an information for all the attendees that we will soon mail you the some link regarding the feedback form. It is mandatory to fill that feedback form to avail the certificate. And we would also, not but the least, we would also like to thank our faculty advisor, Professor Ghanshyam Singh, for motivating us to have such type of webinars. And lastly, again, I want to thank Professor Takar Noori Nomura. So thank you, sir. Thank you so much, sir.
Thank you. If you have any questions, please let me know by email is fine.
De
Thank you.
Definitely, sir. Definitely. Thank you so much for your time, sir. Thank you so much.
Thank you.
So please fill that to all the attendees, please fill that feedback form and we will avail you the certificates. Okay, thank you. Now I'm ending this meeting. Thank you so much. Yeah, there's one message for attendees. I'm sharing that link here only. So please see your chat box.